from AD Academy. In my previous video in this playlist I have talked about activation function, and in the second part of that I have talked about different types of activation function. In this video I will talk about different types of activation function in details, their mathematical formula, how we derive those things, and the application with advantage and disadvantage. My name is Dr. Ayan Debnath. I have secured Ph.D. degree from IIT Delhi in data science. As a visiting research scholar, I also have research experience in Harvard University and University of Pennsylvania. Total 8+ years of experience I have in this field of data science. So let's watch this video till the end to know about different types of activation function with mathematics in depth. Next one is parametric ReLU. Parametric ReLU is similar to that of leaky ReLU. Here this portion is same, and in this portion it is kind of leaky ReLU. In leaky ReLU what I have mentioned is that there are some value to these things, though it is not 0, but there is some value. We can mention it as, say, alpha of x. So we can say f of x is equals to x for all x greater than 0, or this is equals to alpha of x for x less than equals to 0. And this alpha is actually a learning parameter, or you can say is it as a hyperparameter. Hyperparameter means that we have to tune our model giving defined values to this alpha, and generally we take this alpha as say 0.01. Generally we take these things, but it doesn't matter, like every time it will be 0.01 by default. We can tune this value alpha, and as we tune these things, this will shift, this will, but again if it shifts, still also the derivative of this value will not be 0. There will be some value to it, and as a result again it solves this dying ReLU problem. Parametric ReLU, you can consider it as a similar to kind of leaky ReLU. When it will be leaky ReLU? When this alpha is fixed and it will have some default value like that of leaky ReLU. But when alpha is changing, that is we can change this value, it is a learning parameter, then we can take it as a parametric ReLU. Exponential ReLU. This is similar to a variety of leaky ReLU. Here this positive portion will be same. So fx is equals to x for all x greater than 0. But in the negative side there is an exponential thing to it, and it can be written as alpha of e to the power x minus 1. So alpha of e to the power x minus 1 when x is less than equals to 0. So there is an exponential part to it. So one of the disadvantage is that computationally it will take more time if it is alpha x. So what will happen while we are doing the back propagation? If say it is a parametric ReLU, then what will happen while doing the back propagation in this region? If the weight is in this region, so what will happen? Derivative of alpha of x with respect to x will give you this value. So it is very much pretty simple. But in this case what will happen? Derivative of alpha of e to the power x minus 1 by derivative of x. Since an exponential term is involved, so this will be time consuming, quite natural. An advantage, it solves vanishing gradient problem, which I have already discussed. Here there is one thing, one of the disadvantages is that it is a time consuming. If we take the derivative of this function, this one, for this region derivative will be 1, as we already know, and in this region the derivative is like this. This is not 0 but near to 0 but not 0, and as a result it solves this vanishing gradient problem.